Hi guys, Butch here again with the TSA for RE Michael Company. Just want to continue on with our lesson about Fujitsu, our product we brought on here. And I think our last lesson we learned a lot of things. I think we learned we need to use nitrogen to braze, didn't we? I think we did, and I think we need to learn that we can increase the pressure in order to shift the valve if it's stuck one way or the other. I think that we learned that a man doesn't trip over a mountain, he trips over a pebble. We want to look at the little pebbles. We learned about how to test TXVs with superheat and stuff, and we're going to get into charge a little bit, line set. Today we're going to talk about a little bit about some electrical things, a little bit about wiring, not much, and then we're going to talk about airflow. And I think that's going to be probably the longest thing we do today. And so we can understand how these things work and what a motor does and how we move air through a system and stuff and things. I get a lot of calls, and they say it's they tell me they said I got it. You sold me or RE Michael sold me a piece of junk. And I go out there, and next thing you know, I take out 2, 3, 4, 5 pounds of refrigerant, and then it works great. And they go, "Oh my God, the junk's gone! It's wonderful." And the other one, I go out there, and they say it's a piece of junk, and I go out there and look at the duct work, and I'm going, "Oh my God!" And it's just so bad, so inadequate that it doesn't supply the right amount of air across that coil. So we're going to talk about these things. I'm going to tell you a few stories jobs I've been on that have astounded me. But we got things fixed though, and we take care of things because we're watching out for pebbles. Amen. We're watching out for pebbles. So let's get started in about 20, 30 more minutes, and then we'll move on from there. Right? And so we're going to take a look first off at a capacitor. A run capacitor. The unit comes with a run capacitor. A run capacitor increases efficiency. It does. A run capacitor, that's for in state tests, it increases efficiency. As you see how it's wired there, you see it comes off T3. It goes over one side. A lot of contactors have T2, L1 and L2. This one has L1 and L3, T1 and T3, which is fine. And so then you see that main wire on the contactor, the one that's broke, it powers actually the run winding, right? It powers the run winding. And the run capacitor is hooked into the load side of that is hooked into the start winding. You see the start winding is smaller, so it has more resistance, more ohms. And the run winding is larger, and the largest one of all, the thinnest one of all is between run and start. But saying all that, you got to make sure that you hook it in the right place. If you hook that backwards, in other words, you put the start where the run should be and the run where the start should be, what you're going to get half lock rotor amps, and it's not going to work properly because the resistance on the other side. I get a lot of guys call me and they say, "We just changed a compressor, a fan motor, we put the thing on here," and I'll ask them to give me an amp draw. They'll give me an amp draw, and I'll say, "What's the lock rotor?" And they'll say 80 in it, but it's pulling 40. I'll say, "Well, good. Swap the capacitor wires around, and you're good to go." And I'm going to tell you, 99 times out of 100, that's all it is. So just make sure you understand that even though it says run, especially for you new guys, just because something says something doesn't mean it applies to something that's run. That applies to the start winding, even though it's called a run capacitor, right? So it increases what? Efficiency, right? In fact, this is a start capacitor or start assist. Back in when we started doing years ago, 13 SEER, about a little over 10 years ago, 10 or 12. A lot of TXVs came into play, and Carrier and Train and Allied, Linux was saying we had to put all start assist anything with a TXV because the compressors, instead of having a 3 horsepower compressor and a 3-ton unit, became a 2 horsepower compressor, and so it needed a little ump to get it to start, a little help. Now a start capacitor increases torque. A run capacitor increases efficiency. A start capacitor increases torque. And you see it has a potential relay. That's exactly what it means. That you see it's hooked through the T1 to the common, and you see the other side goes to the capacitor, number 1, right? And then it leaves there, it goes to T3 actually, so it's powered that way. Then it goes back up to the run side, and then back to the run capacitor, start capacitor, run capacitor. So that's how you wire one. It's very, very simple. Now we do have at RE Michael things you can just plug into the start capacitor. You ain't got to do all these things. It does have a potential already built into them. A lot of manufacturers will complain about these things, even though I've had no issues with them whatsoever myself in the field for almost 50 years. They work very, very well, and they've gotten better and better over the years. So what this does is help what? and it starts the compressor 100 times faster. Now, sometimes I go on jobs and they say, Butch, this is blinking. I go up there and I look, and maybe it's a 1970s or 60 model home with a 100 amp service. They're trying to do dual fuel or whatever. And it come to look at the wiring, the electrical box, and it's got screw-in fuses and cartridge fuses, and the wiring is old cloth wire so diminished it's unreal. And what you need to do is have a serious talk about their electrical upgrade they need in their home in order to, for safety's sake, right? It doesn't mean that you're an electrician, you're not, but you can give advice, right? And you can also put a hard start or a start assist. That's sometimes you'll hear on Nate question test. Start assist is nothing but a hard start with a potential relay. That it would start faster. Now it's still going to blink. They just can't see it. It's so fast. That's all it is. But it helps you resolve an issue until they can get their electrical system. And advise people when you see something of safety like that in order to get it repaired, whether you're in that business or not. It's nothing worse than leaving a job and having a house catch on fire, something tragic happen, and you were just there. And even though you may have had nothing to do with it, it's very good to advise people when these safety issues, no matter what it is, right? And so wiring, right? And so we want to talk about thermostat wiring to an outdoor unit, from the indoor to outdoor to the air handler or gas furnace. You know, as you see up here, the low voltage control wire should be 18 gauge. Now, if you take some tests, that you could be at 24 gauge, but it's only like 20 foot long, down to 14 gauge, which is 250 foot long. But anyway, you see here, length longer than 100 foot should be 16. So this is Fujitsu's recommendation. And I would always put on a heat pump the outdoor 8 and indoor 8. You never know when you're going to need an extra wire. I've been on many jobs where a wire is broken from the indoor to the outdoor, you know, and then you could find one wire that was good, and now you're not having to pull a whole bunch of new wires. And it might help the guy, your guy who's after you, that comes after you. And so we want to help each other in this industry if we can, I believe. So, hey, let's do that and use that. I would at least put 8 to my stat too. You know, even if I had a straight AC, which only takes 2 wires, I'm going to pull 4 out there just in case I ever have any issues, right? So here's how a thermostat's wired. As you see this thing, this is a heat pump stat. It's filled. You see B, right? Remember? Fujitsu is like Riemann, Rudd, and Bosch. It energizes during the heating mode, and it fails in the cooling, right? It's de-energized in the cooling, not fails, de-energizes, right? So you see the B, and it goes to the air handler and out there. So actually, really, if you look at these things, that's your first stage of heat right there from your heat pump and stuff, and you see where it goes out here, right, to this place right here, right? And then also you would take and you'd say, well, here's Y1, of course Y2 if you have a 2-stage here, and it goes to both and stuff. Depending on whether it has an ECM motor, a variable speed motor, or a PSC motor, the air handler and gas furnace needs to know what speed the air needs to be in. It will know what mode it's in, right? Whether it's in cooling or heating, right? And then you see G, of course, and then you see W2 right here, right? W2 auxiliary, right? And you see E right here with this one. Now also, as you look at this stuff and you'll look at these things, you'll see a jumper up there. Now, not every stat has to have a jumper, not every one. So you got to know your stat. I get calls on stats all the time. In fact, if I took a look at some of these stats, say like I was looking at this, let me turn this right here just for a minute. Let's take a look at this stuff. So let's say I'm looking at a Pro 1 heat pump stat cooling or heat pump. This will do. I think this is their 85 model. Yeah. T6 100, yeah, TH83, right? So it's a touch screen, right? But if you look at this thing and how it's wired on here, you look at this one, and I'm just trying to show you here a little bit how this thing is wired here, and you would see it has an auxiliary and E on the heat pump side. In other words, it doesn't have a W2 R and E. It has an auxiliary E on one terminal. So it's already programmed into this stat, so there's no jumper needed with this stat. No, not at all. Now, not that that's bad. It's not bad, and not that this is good. But Pro 1 has already taken some things to do that, right? In fact, you'll see on this other side, conventional-wise, it's got W2, and then so that would be your gas furnace. But on the heat pump side, it has E and auxiliary on the same terminal instead of W2 and E, right? Now, if you look here at this, and this is what I have, and I'm not going to take it off my wall because it's a T10 Honeywell. No, a T10 Honeywell, which it's Wi-Fi, it's all these things and stuff. And if you look at it, and I say, well, look, it has auxiliary and E, so it would need a jumper, but the jumper wouldn't be W2 to E, it would be auxiliary to E. So what's the name of the story? The name of the story is you need to understand and read, see what kind of stats you got. I get a lot of calls and they say, Butch, my emergency heat doesn't work. And the whole time it needed a jumper, right? And that's it. And then I get another call, where do I put my jumper? Well, you got a stat that doesn't need a jumper, so you don't need it, right? And you can put it on the indoor too, but then you would negate the staging of that too. So anyway, saying all that, just to make sure you understand what stat you have when you start to wire these things, right? So there it is, and you see right here, you see the D right here. A lot of people use E, or W here on the defrost. That is the temperature to defrost the heat, because the unit goes into cooling to defrost, and to give you a little heat so you're not freezing to death while it's going on. I get a lot of calls, especially with our premium brand, our dealer brand, Braun, and with our air temp. And it used to be very bad, but it's a little better now, because they have a W2 in and a W2 out on the outdoor unit, and that's the temperature. The W2 out goes, but the W2 in is on the same side that everything wires in. So guys were wiring it to the end, and it did not work. It would not temper defrost, so they would call and say every once in a while, if I got to get a call, say, Butch, the homeowner says in the middle of the night they'll get up and the air conditioning's on. And what it is that they didn't wire the proper terminal on the outdoor unit to temper the defrost on the indoor, on the air temp and the Braun. So they thought the air was on. The whole time what it was just a miswiring, not following the instructions, not being ugly, because things happen. I've done things myself where they didn't do that. So make sure it's always out, O-U-T, on the outdoor unit when you're taking it back to the air handler, going out the outdoor unit to the indoor unit, going out, not coming in. Right? The in is only used if you don't want to do balance point with an outdoor thermostat. So make sure you understand that if you're putting in air temp or Braun, right? And so now here's a typical dual fuel setup, right? As you see now, a gas furnace has W, right? It's W, and you don't see. Now, if you have a two-stage furnace, it may be W1, it may be W1, W2. Most of them are W1, right? In a two-stage thing. And you have the wiring to your same thing, the reversing valve, all the other stuff, and they got an outdoor sensor. Now, you don't necessarily need an outdoor sensor with all stats, right? I mean, on the one, my T10 that I have in my house, I don't need it because it has Wi-Fi. But if you have a homeowner that doesn't have Wi-Fi, then you would need it. In fact, on this Pro series that I have, you do have an S1 and an S2 sensor. And now you can program it dual fuel by, when I ask you a question, fossil, right? Now, it does have a program inside of it. If it runs too long and doesn't gain heat, in other words, it doesn't start satisfying, it will bring on the fossil fuel. But you have to program that in there. And so does Honeywell too. But a lot of them, it's best to have a sensor. That way, if you have a sensor, you can lock out and you can bring on certain things at certain times with a stat. Now, this one obviously needs a sensor, and the Pro 1 could use a sensor in order to make the unit more efficient and work properly. Now, doing dual fuel, and I was involved with one of the first dual fuels. I was in Mountain Brook, Alabama, and it was a train unit, and it had 1,000 wires and about 5 boards. And it took a day and a half to wire it. I'll never forget. I think I had a full head of hair and was like 28 years old. But it was very much an adventure at the time. And but now these days, I mean, to be honest with you, all I have to do now is push on this one, or even on that one, and put fossil fuel. It'll ask me what kind of fuel, and then what do? You wire it the same way you wire anything else, from a gas furnace to W to all the things, you wire it up, and then when it asks you what kind of auxiliary fuel you want, whether electric or fossil, you push fossil, and that's it. Now, I'll be honest, there's still products out there where you can get a lot of boards and a lot of wires and do a lot of stuff. I'm always a proponent, the less boards, the less wires, the better. The less boards, the less wires, the better. So I'm going to actually try to encourage my customer and my service guys and even you guys to go in there and buy you a good Pro One, buy you a good Honeywell, program it so you're not adding extra wires and doing extra things in order to get dual fuel. It's so simple now, it's unreal. And I think that's one of the great things about electronics now, is we can do things and it doesn't kill us while we're trying to do it or work us to death, trying to figure out more wires, more boards, more stuff, and more things to go wrong. So anyway, fitting all that, that's about where we're at with wiring so far with it in this segment and stuff. So now let's talk about airflow. Airflow is very, very important. I rather test than guess, and you can test airflow, and we're going to look at some of these things. I go on a lot of jobs, and they'll tell me it's a piece of junk. Like I said, I take refrigerant out. They tell me it's a piece of junk. I look at the duct work, and I say, oh my God, look at that duct work. It's amazing how bad it can be. I've had many guys, let me turn this back here. Had a guy the other day said, I took out a 3 and put a 4 in. I took out a 3 ton and I put a 4 ton package in. I said, how was the duct work? He said, what? And I'm not being ugly or anything, but we have to understand when we apply a unit, it always has to be applied to a certain structure. In fact, if I have an air handler in a condensing unit or a gas furnace in a condensing unit or whatever it is, right? And I take out a larger size, I don't evaluate the ductwork. How much ductwork is on the outdoor unit? Well, none, right? None. So if I have diminished ductwork, smaller or even larger, now I'm out of balance. That unit outside, the equipment outside is moving enough air because it's brand new and it's clean, right? So if I don't have enough air on the indoor air handler stuff, then I'm out of balance. So nothing's going to work right. My charge is not going to be right. A lot of things are going to happen. I go on a lot of jobs and I will evaluate the duct system. And sometimes you have to have an honest conversation with a homeowner and about their duct system, their filters, filtration systems, all these things. And I want to have a class on that in about 2 weeks from now. And we're really going to take a look how to evaluate a duct system and come to the place where we can talk with our homeowners intelligently and show them some papers and some engineering information so they can make a good rational decision instead of me just saying it's the wrong size. You understand? Because already homeowners think we're all liars. And so we're not. We want to be honest. I know I do, and I believe that all you guys want to be honest with your homeowners and want them to have a piece of equipment that will work properly according to the charge of the airflow and that will meet the needs of that structure. So let's talk a little bit about airflow. How about it? Huh? So we got airflow here, right? Proper airflow, refrigerant charge, they're absolutely synonymous. You cannot have a proper charge without a proper airflow. It'll never work. Your unit won't be a 16 SEER, 15 SEER, 14 SEER. You'll not have the proper energy, nothing, without the proper airflow. Huh? So to set it up first at 320 to 350, all my life it's been 350 to 450. There's another slide, so don't get confused. It says 375 to 450, and that's okay. But anyway, so we need to have the proper airflow or the charge won't be right. So how do you test it? Well, this is a manometer, right? A manometer or manometer if you live down south, right? And stuff. And what we're checking is the positive, and then that's the positive, and you see this thing is running, and I have a little over 0.5, right? A little over 0.5. And then I have a negative, it's a little over 0.2. Then if I go to the whole thing, I got a 0.7. So now I am testing the airflow according to an airflow chart. And then I'm testing a drop across a coil, which I need to test. I can actually tell if a coil is dirty by testing this and see if it exceeds that drop, right? And so there it is. In fact, you see 28 to 32, 1100 CFM and 32 at 28.28. Pressure drop across it at 1200 at 32. The more airflow across it, the harder the bottom will be more, the top will be less. You'll have a bigger spread. You see, as it gets larger, the more airflow you get. But saying all that, what if I looked at this chart and it said 60, 70, 80 instead of 32 on the 1200 one? What if it said 1 point something? What if it said any of these things? That would mean there's something going on with that coil, something done stopped up, right? So now I don't have to take it apart to see. I can just test it with my manometer to make sure to see that. Now this is actually how you test a gas furnace or an air handler. You get it beyond all the stuff to make sure that air handler, that appliance, that one appliance is putting out enough air. You see 0.7 here. So this is putting out 0.7. Now this is just a test. This doesn't mean this is right. I mean, most units have a thing, well, all units, not most, all of them have a thing, motors have a thing called static horsepower, right? And you'll see that on some Nate tests. And all of them are applied at 0.5. In other words, this unit is able to overcome 0.5 static. It can get more or less and stuff, but you'll diminish certain things. But at proper airflow and proper amp and proper energy, it's going to be 0.5 on 99.9% of the equipment. I think Train one time tried to do 0.3, but it didn't last long, right? So you see, this is what it's doing when it's doing it. So on the top one here, right here, I have a PSC motor, right? You see the low, medium, low, and all the speeds there. And if I just I had that 0.7, so I can say confidently that I have 1195 CFM coming through that unit. Why? Because I had 0.7. I looked at my airflow chart, my data performance, airflow data performance chart, CFM delivery chart, and I have, if I've got a 3-ton unit, I can live with that, can I? Yeah, I absolutely can. It's going to apply. Now, if I got a 4-ton, I've got some issues, don't I? Absolutely, I can't live with it. If I've got a 2-ton, can I live with that? Well, no. In fact, I need to change some speed taps and stuff. And in fact, if I was at 987, I would be a 2.5. If I was, I'd be on medium high at 7. But if I change the speed, I'd also change the static. And you see, the lower the static, the more CFM. The higher the static, the less CFM. So it's not good to get past that 0.5, in my opinion. Now, if I had a 2.5-ton unit or a 2-ton, I could put medium low, and it'd be at 843, which means my unit would be efficient at that, running to 0.5. And I would not be overamping or making my motor do more work than it should. Now the next one down here is external static, and you see it's an air delivery, but you also see the motor, and it says it's a half horsepower. That's the size of the wheel, and then you see 1, 2, 3, 4, 5. So this actually is an ECM motor, but it's got a little taps right here of 5 speeds on this stuff, right? And so you see the static on here. The constant torque motor has a static. The variable speed does not have this. So, and it was about, whether you plug it in or whether you use a board with dip switch to setting. But you see 0.7 with this particular unit is 1141, right? And you see the higher the static, and you see it goes up to 1. Now most tests, Nate tests and state tests, will tell you that they'll ask you a question: what is the highest static on a blower performance chart? And the answer is 0.8. Is 0.8, right? A lot of guys put 1.0. That's not the right answer. ECM, yes. PSC, no. So make sure you understand that. So how can we do things? Well, you got a heat rise, right? We have a heat rise on these things, and you can do that. I do this all the time. Of course, these guys have put a little more in there as far as most of the stuff we use. You can get amps times volts, and then we got to get BTU output, right? Now this one has some other stuff like a 3-phase formula, which we'll probably never use, but it's good to know if you're in the commercial. Times 0.59, which means it's 3-phase. 0.108 is called a correction factor, and it's always there. Anything below 1,000 foot of elevation, you get above 1,000 foot, which none of us down here in Alabama are. You'll never use anything. Some of them are 0.1, which means it's just equal to whatever it is. So you got a delta T times the 0.08. Now remember that delta T, your temperature difference of 0.08. This is not very complicated at all. In fact, if we move on here, I can show you some things that I do all the time as a tech guy and helping you guys do stuff. And I use this formula constantly, right? In fact, you see this, it's 240 times 40 times 3.413. Now, some manufacturers and some engineers use 0.314, right? 3.4 3.414. But this is point, and that's just no big deal. So now I get the BTU output, right? So I've got my voltage, whatever my voltage was here. And let's say this one was 240 times 40 amps. And then you said, well, I got my watts, so that gives you watts. Amps times volts equals watts. And then I times that by BTU. So now I've got my total BTU output, right? At 32,765, right? And so now I do a delta T. So now what did I do? I got amps times volts, right? Equals watts times 3.413. Now I've got my total BTU output, right? And so now I got to get a delta T. I went in at my return, all right, at 70. I came out at 107. So now I've got a 37 degree, right? And so now what do? Well, I just take that 3,000 and I take that 37, right? I take that 37 and I time it times 1.08, which gives me a 39.9. And I divide that into 32,765, which gives me my total BTU. So let's do some change. Let's say the amps and the volts are the same, but let's go up. Let's say now instead of 37, we have 47. We have 47. Now we understand that right now this air handler, our gas furnace BTU output is moving because we tested it, 821 CFM. But now let's change the delta T. The delta T is now, instead of a 70, it's 117. So now we're 47. So I'm gonna go times 1.08 equals. Now I'm at 50.76, right? So 50.76. So I still got 32,765 BTUs divided by 55.76 equals. Now I've got 587 CFM. This increased 10 degrees, and I went from 821 to 587. And now, I want you guys to understand this very well, because I do this all the time, riding down the road. And now that you understand it, you can do check amps times volts, right? Times 3.413. Get your delta T and determine exactly how much airflow is coming through an electric strip heat furnace. If you got BTU output, let's say if I got a 100,000 BTU gas furnace at 80%, well, that's 80,000 BTU output. I can do the same thing with that. It's all about BTU output. Then what? Delta T. BTU output, delta T, right? 1.08, below 1,000 foot of elevation, right? That's your correction factor. Times it, then divide it. Times it, divide it into your BTU output, and you're done. Then you know exactly how much airflow. The last one I went to was way up in Decatur, Alabama. And the guy, they'd been out there 10 times. I did one with 20 kW. I didn't put it on high. I always want to know what it's doing when it's doing it. Let me say it again. You'll get a lot of training. They'll tell you put it on high to C, A, B, C, or D. Well, we're trying to fix a problem, right? An issue. So what I do, I leave it exactly like it is, and I do the test then. Then I can determine if it's what it's doing when it's doing it. Now that's pretty good. That's testing. That's not guessing. I think the airflow is good. I get that all the time. You don't have to think. I can do a heat rise and know exactly what it's doing, right? And then I can apply my refrigerant charge and all the other things to the structure that I'm trying, or the problem I'm trying to resolve. The last one was that the delta T on electric strip heat was like 62, which is outrageous, right? It turned out he had a 5-ton drive furnace with a heat pump, right, with 20 kW in it, but it was in a mobile home. It was in one of these modular homes. The duct was so diminished, the return was so small. Listen to this: 2 CFM for 1 square inch, 2 CFM for 1 square inch for filtration, and that's in every book you can ever find. And so if you got a filter and a grill, and it's 5-ton unit, right? So you got 2,000 CFM, so you need 1,000 square inches. A 20 by 30, what gives you what? 600? So you need more than that, don't you? To make sure the unit is working properly, that's how you do it. Yeah. So make sure you understand these things. And then when we do our airflow class, I'll give you some of this stuff so you can print it off and have it for yourself, and you won't be out there just telling people things. You'll be able to show them engineering information. So make sure you remember that. What I got? BTU output, right? What I got? Correction factor, delta T times 1.08, right? Divided into that BTU output, and now you can always test your airflow and never be guessing. You can always be testing. Amen. Okay, there you go. So let's finish this up a little bit. I know I've been going on a little bit, but it's very important, right? The same thing if you're doing a gas furnace. Here it is right here, a gas furnace. It doesn't matter as long as you have BTU output, you can determine, right? So high temperature drops across coils, low superheat. If you don't have your airflow right, there's going to be a lot of stuff. Your superheat will, if you don't have enough airflow to go to nothing, you got too much airflow to go way high, and you have to understand that this has an effect upon all this stuff. And so you got to be very, very careful with airflow in order to get your charge right, right? So, saying all that, let's see how long we've been going here. 30 minutes, wow! I'm going to stop right here, and I'm going to tell you what, we're going to get into piping and charging next. I think it's one of probably my second call. The most call I get is piping, and well, actually charge, because they overcharge usually, especially with microchannel or product, the air temp. But understanding air temp, the microchannels, I got a lot of customers very, very successful because they make sure they take care of the little nuances. And I know even with Fujitsu, you take care of the little things and it'll take care of you. Right? Now, we at RE Micro want to help you any way we can. Call our branches, ask it, go online, get our training. There's lots of websites with training, and I'm going to have just one day devoted to just getting you the right information to get the training you need in order to be successful. Don't forget, we care about your success, because we're not going to be successful unless you're successful. So give us a call if we can help you in any way, and I'll be seeing you shortly.